Good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes, an electrical engineer by profession. Okay, and an electronic troubleshooting concentrated on the hands-on troubleshooting. Okay, let's proceed for this afternoon. My topic for this afternoon will be lesson number 95 on my channel. It is under the topic integral calculus. Okay, and the main topic will be under integral calculus. There are so many chapters in integral calculus. The topic for the meantime is surface of revolution. Surface of revolution, something like, okay, if this is a curve, then we try to rotate this one with respect to the x-axis. Okay, it will generate a surface area, and that is termed as actually surface of revolution. The other case is if we try to rotate this line here with respect to the y-axis, it will generate a surface area, and that surface area is still surface of revolution. So there are actually two cases over here. If we try to rotate with respect to the y-axis, it will be something like this. And if we try to rotate with respect to the x-axis, it will be something like this. Surface area, it's not so complicated, unlike on the volume. Surface area is just the product of a unit length and a unit length. It's the same in the so-called area, but this is referred to as surface of revolution. It is still an area. Okay, let's proceed. There's a note here under the so-called surface of revolution. A surface of revolution, I will try to read this. Okay, this is the foundation of the surface of revolution concept. A surface of revolution is generated by revolving the arc of a continuous curve about a line in its plane called its axis. If we got an arc, okay, then we try to rotate this arc one complete revolution with respect to the x-axis for the meantime. Okay, you cannot rotate this one with respect to the y-axis. If you try to rotate this one, okay, it will create a surface of revolution. Okay, the other case will be something like this. If this is the curve, okay, an arc or a curve, then we try to rotate this curve here. From this point here out to this, we try to rotate this one complete revolution with respect to the y-axis. It still creates a surface of revolution. Okay? That's the meaning of these wordings over here. That's the concept of the so-called surface of revolution. So actually, we are given the this is not after the completion of the revolution, we are now on the so-called XYZ plane. Okay, so if we try to bring up the figure for the meantime, this is the x-axis, this is the y-axis, and this is the one in red is actually the curve. We call it length of arc. From this point here up to this, it is a curve. Termed as arc, okay? Then if we try to rotate this arc for the meantime, one complete revolution with respect to the x-axis, okay? The problem is, what will be the total surface area generated? Okay? Also, this applies to the so-called big dome, okay? How the engineers will compute the total roofing to cover up a big dome. Okay, that's the importance of the so-called integral calculus. Okay, let's try to bring out the two cases under the surface of revolution. Case number 1. If the arc or equation is revolved with respect to the x-axis, okay, total surface area with the subscript x, this is subscript, equal to the integral of 2 pi y times ds. Why is that so? Because if we try to rotate the arc or curve with respect to the x-axis, then we try to spread it out. This will be the area. This length here is the circumference. Okay? Circumference. And the formula for taking the value is 2 pi y. And what is this arc? Oh, that's the arc of the given equation. The one being mentioned, right? It is d small letter s. This is capital letter S. Total surface area will be represented by total capital letter S, and small letter s will be the arc of the required figure. So formula number, the resulting formulas under case number 1, there will be 2 cases. Because in the computation of the arc, there are actually 2 variations. It is this. That was the topic the last time around. Okay? To compute for the length of arc from this point here to this, case number 1 is actually this one. We did this the last time around. Differential length of arc is the square root of 1 plus dy dx quantity square times dx. Or the second equation, second variation, differential length of arc will be equal to the square root of 1 dx over dy quantity square times dy. So actually, I presented 2 formulas under case number 1 because in the computation of differential length of arc, there are 2 variations. So actually, the total surface area, if it is rotated with respect to the x-axis, that's the meaning of the subscript x over here, equal to 2 pi, the integral from a to b of y. It is this. We are following this. 2 pi y is this, times ds. So the product of ds and circumference is the total surface area generated. We spread out the surface area so we could visualize it. So this is 2 pi, it's outside, the integral from a to b of y, the square root of 1, dy dx quantity square times dx. Second formula, it's still the formula or the surface area is rotated with respect to the x-axis. This is 2 pi, the integral from c to d of y, still the same y, times the square root of 1 plus dx over dy quantity square times dy. This is dx, this is dy. Because in the computation of the length of arc, there are 2 variations, right? For the first one, the upper limit, lower limit is a, the upper limit is b, the radius is y. Okay? It goes here, this one. The radius is y. Meaning under this formula, lower limit is a, upper limit is b, radius is y. Second formula, with respect to dy, lower limit is c, upper limit is d, and the radius is still y. Okay? This is y. Okay? Because we rotate the arc with respect to the x-axis, so its radius is actually y. Case number 2. You just change this one, try to figure out that it is actually to be rotated with respect to the y-axis. The total surface area with if rotated with respect to the y-axis equal to 2 pi x. Because if it is rotated with respect to the y-axis, if this is the curve, the radius will be x, right? So this is 2 pi x times the formula for taking the length of arc. Two times. It is with respect to x, the first one, with respect to y, the second one. So on the first one, the upper limit is actually b, lower limit is a, the radius is x, if it is rotated with respect to the y-axis, okay? For the second one, different limits. Because we are integrating with respect to y, so our limit should be ordinates. It should be lower limit is c, upper limit is d. Why is that so? From the first point, x is equal to a. Second point, x is equal to b. So under case number 1, the limit is from a to b. And if we are integrating with respect to y, the first point, y is equal to c. Second point, okay, y is also equal to d. So the limit, if we are integrating with respect to y, should be the limit, okay, from d, or from c to d. This is from c to d. Okay? The limits here are abscissas. The limit here are ordinates. This is all also ordinate. So there are actually 4 formulas. Just remember the first one, then take the reciprocal of the second one, you could bring out this one. Even the second formula. Okay? Just remember this one, and to bring out the second one, just reverse this one, but this should be multiplied by 2. Okay, that's the so-called concepts under the so-called formulation and how to take the surface of revolution if a certain arc of a curve will be rotated with respect to the x-axis, or if it is rotated with respect to the y-axis. Okay, that's the concept of the so-called surface of revolution. Oh, good afternoon, Los Angeles.